Hello and welcome to this episode of Reviewing Key Engineering Plastics. My name is Herwig Juster and today we are going to talk about Polyamide 6 and Polyamide 6.6. We will review the chemistry, including a look at the simplified petrochemical flowchart, discuss the properties of polyamides as well as the global demand on producers. I will provide you some price indication and we'll talk about the end users of polyamides too. So let's get started. Before we start with the chemistry, I would like to spend some words on the history of polyamides. Welles Carrotiers, working 1930 at the DuPont company, developed together with his assistants the two most widely used synthetic polymers of the 20th century, polyamides or nylons and neoprene, synthetic rubber. We will focus in this review on PA6 and PA66. On this slide you can see a comparison of those two. Although quite similar, there can be some differences found in the glass and melting temperatures as well as the water uptake, which is for polyamide 6 higher. Where do polyamide 6 and polyamide 6.6 have their roots? In general, one can state that 95% of the organic chemical industry is based on 7 raw materials: ethylene, propylene, C4 olefins such as butenes, butadienes, benzene, toluene and xylenes. Those 7 starters can be obtained by steam cracking of, for example, naphtha. Polyamide 6 is made by ring opening polymerization of E-aminocarbolactam, which is obtained over the benzene route. You can see here from benzene over cyclohexane to caprolactam. Cyclohexane is first converted to its oxime. An oxime is a chemical compound with a carbon-nitrogen double bond. The word oxime is simply a combination of the words oxygen and amine. Treating the oxime with acid initiates the so-called Beckmann rearrangement to obtain caprolactam. Around 5 million tons is the global demand on caprolactam. Polyamide 6 can be polymerized using hexamethylene diamine and adipidic acid. Both have 6 carbon atoms, leading to the nomenclature of 6.6. HMDA can be obtained over 3 routes: from adipidic acid route, from hydrogenation of acrylonitrile, and from hydrocyanation of butadiene. Okay, let's continue with the properties. Polyamide 6 shows good toughness at relatively high 80 degrees C temperatures and low temperatures as well, and has resistance to repeated impacts. This is rounded up with good resistance to abrasion and wear. Chemically, PA6 has resistance to many organic solvents, oils and gasolines. In comparison, polyamide 6.6 can be used at higher continuous service temperatures, so 100 degrees C to 120 degrees C, combined with a better retention in stiffness, tensile properties and peak temperatures. Capacity and global demands. The total consumption of polyamides in 2016 was around 7.5 million tons. Nylon 6.6 has a consumption of 2.4 million tons and nylon 6 of 5.1 million tons. 70% of the global nylon 6.6 consumption was used in the automotive market. Half of the consumption of nylon 6 is used for producing fibers. Geographically, you can state that Asia is the largest market for PA6 and it is preferred when flexibility and barrier properties are important. North America is the largest market for PA6.6 and is mainly selected for engineering thermoplastic applications due to a higher melting point. Important to note is that both nylons are interchangeable for most applications. Price to performance ratios. Polyamides are forming the base of engineering thermoplastics and have a price range of 2.5 euros per kg for base grades, and high heat nylons can reach up to 6.5 euros per kg. End uses, as previously shown, nylon 6 is more selected for fiber applications such as tire cords and filaments for fishing lines. Nylon 6.6 with a glass fiber reinforcement of 30% to 33% is used in many automotive applications where the combination of elevated temperature, toughness and long lifetime is needed. However, there are many other industry fields where the properties of nylon 6.6 can play a key role. Important to note is the water uptake of nylon 6.6, which can be 2.5% at 50% relative humidity. Nylon 6 has with 2.8% a bit higher water uptake. The water uptake results in dimensional changes, reduces the real stress around 29% of its original value. Elongation will be increased with the factor of 5 and toughness will be doubled. Overall stiffness can decrease almost 60%. Now, what are the typical applications? Just to name a few: belts in cars, guitar strings, and heavily in automotive car engine upper intake manifolds and engine supports mounts. This was a review on nylon, an important engineering thermoplastic used in many applications. I would like to thank you all for watching, and please leave your comments below to share your experience with nylons, and if you liked it, please share and leave a thumbs up. Thanks, until next time.